We're joined by Alex from Graphcore. Really looking forward to today's talk, actually. I must admit, I hadn't been aware of Graphcore before being introduced to Alex. Looks like a really interesting company, really interesting project where they're basically architecting a new processing unit specifically for ML. So really interesting to hear what Alex has to say there. In terms of Alex, he comes from a background as a particle physicist. I believe he's been with Graphcore now in commercial role for 1.5 years, where he works as a senior field engineer there. So I'm going to welcome Alex. So if Alex, if you could turn your camera on and come and join me, that'd be great.
Right.
Yeah, we have audio, we have video. This is perfect. We're in a good place, man. So, as I said, it's quite a short intro that I always do. So, when you're ready, I'll actually get you to share your screen and perhaps give people a bit more of a bio about your background, and then I'll leave you to get into your presentation. And as I mentioned at the start there, I'll jump back on when you're finished. So, if you're happy, I'll leave you to it now. Cool. Enjoy it, everyone.
Thanks. My screen share sorted. Hope everyone can see that. If the screen share doesn't seem to work, or if you can't hear me very well, do let me know. My fan's on, so hopefully it won't cause any audio issues, but it's 600,000 degrees in here, so I'll have to leave that fan on, I'm afraid. Okay, yeah, so as David said, I'm been working at Graphcore for about 1 year now. Before then, I was a particle physicist, PhD, with the University of Bristol, University of Southampton, and also worked a bit at CERN in Geneva, so that was a bit of fun. But yeah, so I'll get started with our sort of talk here. So yeah, Graphcore, I'll tell you a little bit about sort of the what, the why, and the how of all the things that we do, and give a bit of a motivation and explanation as we go along. Okay. So the first thing we sort of start off with is that we want to get some machine learning type innovation going, but really, what's the real kind of connection, I suppose, between a silicon processor and something more like the brain that we know obviously does an awful lot of learning tasks quite well. And as was summarized quite nicely by Jeff Hinton here, the main idea is that we need to move towards a very different kind of computer, different kind of processor entirely. And in a rather slick fashion, he then pulled out a Graphcore processor, IPU processor from his pocket, which is quite nice. So yeah, so what are we talking about when we say machine intelligence, machine learning, this sort of thing? And today you normally think of what we see on the left there, which is, you know, is it a cat or not? Was it a hot dog or not? And this sort of thing. And it's relatively basic in some ways, although it obviously is very, very powerful as well. But where's it sort of heading? Where are we going with all this? And is it something that's really scalable with current architectures? Or is it getting to a point where we're just trying to brute force bigger and bigger computations? So the main thing we notice is that the size of the models in terms of how many parameters you've got, as well as one sort of measure, is growing ridiculously so, really. But large down here, I don't know if you can see my mouse, but in the middle there, that's quite a big natural language processing model. But even then, compared to some of these other models here, we're really getting to sort of much bigger scenarios, and really to try and brute force that by just building bigger and bigger supercomputers to attack it. Is that really the way forward? Recently, Facebook have claimed they had a 2.5 gigawatt capacity power supply for their big data centers, which, to give you an idea, that's about 5 nuclear reactors worth. So really, if we're going to be spending all that kind of power, it's getting to the point where to train a model is costing an awful lot of money, energy, and everything else as well. So it's not just do we have the computational power to do it, but also how efficient is that? What's it really costing to do that computation? So clearly a new approach here is required, rather than just building bigger and bigger processors of existing architecture. Apologies if you can hear some music. There's a chap who likes to ride around our neighborhood every so often playing very loud music on his bike. Today it seems to be reggae. Last week it was Iron Maiden. He changes every day. It's quite nice. He's gone now, I think. So, so yeah, we're looking at a very different type of compute workload for which we want a new kind of approach. So what are the kind of features we really want this to exhibit? So clearly, if we're going to distribute an awful lot of different computations around, massive parallelism is sort of a given, really. Data structures being fundamentally sparse is quite an important one, really. Not all parameters are going to connect to all other parameters necessarily. Low precision, yeah. So in a lot of cases, parameters in these models don't really need to be super high precision. So is there sort of a bit of inefficiency there as well? And can we utilize low precision variables in order to massively boost performance? Parameter reuse in models. So once loaded into memory, can we reuse a lot of parameters again to give us a much more efficient scenario? Static graph structure. So fundamentally, a lot of compute graphs are static. Like in a brain, you wouldn't go rewiring the entire thing just to do a slightly different task. So there's clearly some level of static graph structure there. And finally, we talk about entropy, which is like noise. So a lot of models benefit from some amount of injected random noise. Like say for dropouts, you want a good way to generate some random noise. So perhaps if we could maybe generate efficiently random numbers built into the hardware, that would be really useful. And that's a little bit of a spoiler before I get on to what our hardware actually does. Oops, I'm on the wrong window. There we go. So as we say, legacy processor architectures, CPUs, GPUs that we're all quite familiar with, they've been repurposed for machine learning and AI applications. They haven't been designed for them. So it's not to say that they don't work, and clearly there's a lot of cases where GPUs do give you quite a big boost over CPUs for the right kind of task where it can be parallelized and vectorized, but it doesn't mean that that's optimal or really what it's supposed to do. It just happens to be a little bit better than that than others. So this is where we introduce the new kind of processor, IPU. It's the intelligence processing unit. And the idea is that this is designed from the ground up with AI kind of graph models, hence Graphcore, in mind. So looking at a traditional, sort of more familiar kind of parallel machines, this is more like a GPU here. It's what we call SIMD, so it's a single instruction on multiple data. So you want to do one operation on one bit of data. Well, you can parallelize that and do that same operation on a huge array of data quite effectively. That's all well and good when you only want to do that one operation. You want to vectorize everything. And this gets more efficient when you're doing one instruction on quite a long data vector, but there's still a relatively small number of processes in the grand scheme of things. So if you've got large mini batches, large blocks of dense data, then it can be quite efficient, but that's sort of really where it does its job particularly well. That sort of suits what it's designed for. That's not necessarily the case in a lot of computations. So really want to address this as a sort of fundamental design philosophy in a sense. That's something that we think a different idea would be a lot better. Another aspect is memory bandwidth. So if you're going to be doing an awful lot of computation on an awful lot of different parameters, loading your data through, updating a lot of parameters, you really want to have these parameters accessible very, very quickly. So it's down to this memory interface in the middle here, through which your processor talks to the memory and says, right, I want that variable, put this one back, and so on. So if we want to make this an awful lot faster, how are we going to do that? So we see here, so of course, I have my Robinson squash. On the left, we have what we'd expect a normal, if you're building a PC or something, you'd be quite familiar with this idea that you got your processor over here, your memory over there, and there's a limited bandwidth in between them. And this is with relatively new DDR4 kind of memory chips as well. The next one along, we have, this is the direction that a lot of GPUs are going to now, which is high bandwidth memory nearby. So it's not necessarily right next to where you want to do operations, but it's a little bit closer, you got higher bandwidth, and it's sort of somewhat distributed. If we head over all the way to the right here, we see that we've got SRAM, very, very fast memory on chip. And if we have one kind of processing core with its own local memory next to it, and we have a whole load of these in a huge array, then all of a sudden you've got an awful lot of memory bandwidth. And you've got a processing core that could be doing an operation with the memory having all those variables that you're doing the operation on stored right on site. So if you think of this now as having CPU on the left, scalar processor over here, memory over there, GPU a little bit more distributed, but there's still bandwidth kind of bottleneck here and there. And on the right, we've got the IPU, where we've got a huge amount of these parallel cores, each of which has its own local memory. So you no longer have to keep moving things around before you can do anything with them. The data is where it needs to be at the time that you're going to do something with it. And this gives us an enormous, speed up in terms of memory access over the other approaches. So in order to speed up the kind of compute we want to do, we want to have some dedicated hardware for the kind of operations that will be typical of this kind of scenario. So there's an awful lot of matrix operations, dot products, convolutions, that sort of thing. And then we've got things like our activation functions, for example, so like log, exponents, all sort of sigmoid, and all the typical usual suspects there. So these we want obviously to have be included and be very well optimized. Also, we want support for float 32, so your single precision floats when we want quite high precision, but then half precision float 16 when we want to get a good speed up. And then this spread across 1216 independent processor cores. So each of these cores has its own local memory and also has, we'll go into in a minute, 6 threads. So we've got an awful lot of power there. So the whole thing is spread out very, very much, but these are independent cores in the sense that they can do very different things to each other. So we're not talking about SIMD anymore, single instruction on multiple data. We're talking about MIMD, multiple instruction on multiple data. I can do this operation on that data, and at the same time over here, do another operation on that data. And they don't have to wait for each other or even communicate if they're very different things. So, so you're not limited to vectorizing one operation. You can very much do very different things on different data at the same time. And then when we have things like less structured operations, say sparse operations, imagine sort of a sparse matrix, you've got an awful lot of things in the middle that you don't really need to do anything with. If you have to vectorize that, you end up just filling things out with zeros and doing an awful lot of 0 times something or 0 times 0, which isn't very efficient. If you can do a more sparse computation, then you can be a lot more efficient with this sort of thing. But that kind of requires being able to do different things with different data at the same time. Okay, so yeah, to sort of summarize that idea, we want highly parallel, often sparse, and large amounts of floating point arithmetic. And then also, if we're going to do a whole load of these operations, at some point they're going to want to communicate with each other. You know, maybe this operation will act on the result of this and this and this. So you want those to be able to talk to each other quite well. So we want an awful lot of connectivity between the operations. So between all of these different cores and all the memory on each core, you want very high bandwidth. So we need an awful lot of communication required. And that's where the IPU comes in. So the idea is we have our chip with all of our different cores with their own memory. So we call that a tile. It's a core with 6 worker threads and its own local memory. That's one tile. The code and the data you're going to run on in that, say, that batch or that step is stored in the SRAM on the chip. So it's all ready to go. It's all where it needs to be to get going straight away. And that gives you very, very high bandwidth. From then we have our parallel programs, all independent. So we have 7,296, so remember 1,216 and 6 threads each. So an awful lot of threads, all independent. And on the right, we'll get into in a moment, is our SDK, our software stack, which allows us to interface with all this and take advantage of it. So the magnifying glass out and have a look at the schematic of the IP processor here. So like I say, we've got over 1,000 cores, each with 6 threads, so memory. Works out about 300 meg total memory across the chip, but that's distributed across all the tiles. Very fast PCIe Gen 4 access. And then between these, you also have, if you have an enormous model that you want to spread across many chips for efficiency, then you have very high speed links between IPU chips as well. So this is sort of one IPU processor here. You could run a model utilizing many of these, and they can all talk to each other without having to go back to the host and then back to the other chip again. They go straight to each other, which is a lot more efficient as well. And I see testimonial. Oops, I've gone too far there. Testimonial there from Citadel, who are they've been doing an awful lot of micro benchmarking with our hardware, and they found some some big performance there, and they've really kind of dissected it very much. And you can find the archive link there. They've gone to great detail on exactly what kind of performance they can get. Very low level things like copying data back and forth to sort of things that would build up into real world performance. Okay, so these two chips we have located on one PCIe card. So that's how you would see it if it was plugged into your server. And this gives us high performance 200 teraflops of mixed precision computing at sort of very standard 300 watts. That's for one card. And across that, you've got 2 lots of 1216 independent IPU cores, or tiles we call them, each with their own local memory. And then between these cards, we have IPU link connectors, which gives you very fast chip to chip and card to card communication without having to go to the host and then to another card again. Okay, so as you can see, yes, we've developed a new kind of hardware that lets innovators create the next generation of machine intelligence, as the slide says. So that's sort of what we've been doing, but who are we really? We've just sort of turned up with this chip and told you what's in it. So we've been around for about 4 years, almost exactly 4 years actually. Based mainly in Bristol, that's the big HQ, but we've got offices across the world now in Palo Alto, in Oslo, London, Cambridge, Beijing, Taipei, lots of new offices, about just over 400 people globally. And we've got quite a few investors, raised quite a lot of venture capital money already. So here we are, we've got people working from home in all of these locations. I think some people are starting to go back to the office now actually, but yeah, so obviously a lot of us have been working from home for quite a while. I still am. You can see my lounge here. I'm hoping my home Wi-Fi will stand up to this kind of connection, but if I do drop out, do shout and I can always go back and repeat. Okay, so yeah, a little bit about us. We've said about the IPU hardware and a little bit of what it's sort of built up of, but that's not always we don't sort of give a hardware and say get cracking. There's a whole software stack that goes along with this that allows people to take full advantage of the hardware itself. They might come along with an idea of a model they want to build up. They might come along with an existing model or something else they want to do. So we have a whole stack of software that can support all of that. And talking of which, let's get on to a little bit about that software. So I'll just advance all of this. I forgot to get the animation, and they don't really work very well on Zoom. So our entire software stack is a little bit like this. So on the far left here at the top, we've got your more familiar kind of frameworks in Python that you might be using for machine learning projects. So TensorFlow, PyTorch, Onyx, that sort of thing. We want you to be able to use your existing models and import them into our SDK and run those. This then talks to what we call Poplar, which is our graph toolchain. And that goes through, we have lots of different graph libraries, optimized functions for the IPU. And this creates a compute graph, compiles the graph, and then runs this efficiently on the IPU. And then also allows you to visualize and debug the performance and see, you can see all sorts of things like processor cycles and the amount of time it's spent computing versus doing data exchange back and forth and that sort of thing. So this really is sort of the translation. And you can go into, from TensorFlow, we have our own port of TensorFlow where the operations behind the scenes are optimized for the IPU, but also Poplar itself is a C++ framework, so you can write programs in that as well if you want to get down to the metal fast performance. So here Poplar creates this compute graph and compiles that and optimizes things how they need to be to take advantage of the processor. And within that we have these library functions, or these libraries which include a lot of functions. These are just a few of the examples. So poputil, the utility functions for building up the graphs. We have pointwise reduction operator functions, linear algebra kind of functions, random number generation built into the hardware, which is like I say, with if you want to inject some noise or any kind of anything where you want some random noise, random numbers, synthetic data, anything like that, the random number generation is in hardware. And we also have the typical neural net type functions, so activation functions, pooling, loss, that sort of thing, all optimized for the IPU. And to get it to run efficiently in parallel, we have, we can say here that it's the world's first bulk synchronous parallel processor. BSP, bulk synchronous parallel, is a technique used in a lot of big compute clusters where you've got lots and lots of separate CPUs, but it's never been done in one processor on one chip before. And the basic idea with this is that you do your computation, you synchronize between all of your separate cores to say, yeah, that's all done, what state they're in, and then you do the exchange where you say, okay, the results of these, whatever these are doing up here, needs to go there because that's going to do something else with it next, and so on. So you do all the exchange to get the data where it needs to be for the next step. As you see here, even if you have multiple IPUs, that still works because you can do your computations, synchronize between the tiles, or the cores of the tiles on the chip, and then also synchronize between the chips as well. And then you do your exchange, send some data to it from the host, you send your result back, send your next load of data through, and so on. Okay, and yeah, as you see here, you can have an awful lot of tiles all doing this. Okay, and as a basic example here, all we're going to do is take a 4-element array and add up all of those elements. So what we do here, time's going downwards, we communicate first and say, right, okay, let's put these 2 elements, the top left, 0 and 1, onto my first sort of compute vertex. So this will be running on one core. The other 2 elements, 2 and 3, will run on my other core. Each of these will have an output. It will just add up the 2 elements that came in, spit out one number. Each of those will be put onto one core, added up again, and away you go. And in between here, we'll have a communication where you're moving them around, to compute where you add them up, communicate again, and compute, and so on. And that's all done behind the scenes on the chip. And in between those, you'll have a sync each time to say, right, I'm done, that's ready, and so on. And in a much more complex kind of operation or model, you'd see a bit more like this. So this is, there's a lot of dark blue here, so that's a lot of compute work being done. Then we'll have some yellow for exchange. There'll be times when the tile's syncing, but also a time when the IPU is syncing as well. So maybe between the 2, between the host and so on. You get more than one IPU, they'll be syncing with each other as well. So within Poplar, we've got an awful lot of source access graph functions. So if maybe you're working quite low level, sort of real bare metal kind of performance, and you want to build up your own custom operations from the bare sort of the fundamental building blocks. So things like map, mul, convolution, and so on, built-in functions that are all very much optimized. But these are built up of compute elements. So these things like reduce, add, initialize as 0, and this sort of thing. And you can go down to those, and you can build up your own functions as well. So you've got an awful lot of control over that as well. So that's gone into sort of the Poplar side of things, but we have on top of that our own TensorFlow port, and we have PyTorch support on the way as well. That's really getting somewhere now. So we're talking about TensorFlow here, at least for now. I'm sure a lot of you are familiar already, but a very popular Python framework for deep learning and the new algebra stuff. We have our own Graphcore port of this, and that's been tailored for efficiency of a lot of the existing and next generation algorithms for the IPU. So a lot of the functions, you call it the same, they look the same, but behind the scenes we'll have our own implementation that really takes advantage of the different architecture that we're using. Way over to the right, the other end of the scale, we have Poplar, like we say, which is the C++ down to the metal. You can even write some assembly if you want to get really, really serious about that. In the middle here, we've got the case where, okay, maybe you use a slightly different framework or something. You've got your model, you say, well, it's not TensorFlow, it's not PyTorch, but I want to run it in the IPU. How am I going to do that? We also support the Onyx file format, which you can export your model to and import it using PopArt, which is the Poplar Advanced Runtime. And that allows you to interface to Poplar from a model that's been defined in another kind of framework. And that supports both inference and training. And for now, we have quite a lot of examples on our GitHub, which will be a link to the next slide, of all the different kind of, or some of these different categories of application. So that's from natural language processing, we have some BERT examples, image video processing, both ResNet, the sort of the relatively standard, quite well-known image processing model, and also ResNext, which is a next generation model, which I'll talk a little bit about in a moment. We have time series analysis recommenders, so that we have an autoencoder, which we train on the Netflix data set, so that the if you like this, you might like this kind of idea, and also some MCMC probabilistic models as well. So there's lots of different examples there. I'll show on here as well. We have some full model examples like that in some Tentacle, PopArt. We have some more advanced, and also some starting off code examples in PopArt, TensorFlow, and Poplar as well, if you want to do some C++, with lots of different sort of examples of this application, or how to do this on the IPU, how to take advantage of that, and so on. And all of these are on our GitHub already. So as I'll show now, the IPU is able to take advantage of this new architecture to give state-of-the-art performance on leading edge models. And I'll show you just a few. I won't go into too many benchmarks. We'll all get quite bored of them quite quickly. But I'll show just a few here about how we're really able to push the performance. So ResNet, like I say, it's a fairly standard, sort of very well-known image processing algorithm. But here we're seeing higher throughput, but also quite a lot lower latency, which, depending on what you're using your image processing for, quite often latency is very important as well. And here, it's the IPU versus a popular competitor GPU. We're seeing both high throughput and lower latency at the same time, which is great. But really, what we want to do is look at not the old generation models, not old, not the standard, the current, likely optimized for GPUs, because that's been what people have been used to running things on. We want to say, well, okay, how about the next generation of models? If we started looking at models which are a bit different in their construction, things that the IPU can really take advantage of, the GPUs perhaps can't so much. That's where we'll really see a much better performance lead. So an example here is separable and group convolutions, which pose a little bit of a problem for vectorized SIMD processors like GPUs, but they actually really suit the IPU quite well. So just to go into a little bit of detail here, the group convolution, you've got a big convolution operation, and then you split this up into lots of different ones, because the idea is that they don't necessarily, all the parameters interconnecting don't necessarily do an awful lot anyway. Quite often you find if you separate these out, you can get very high accuracy and end up with fewer parameters at the same time by not having the parameters related to how these separated convolutions depend on each other. If you separate them out, assume those dependencies are zero, got much fewer parameters, but often you can end up with higher accuracy as well, or at least higher accuracy per number of parameters. So the tricky bit here is if you've got a whole bunch of different groups, they don't have to be the same depth or anything else. They can be very different operations, really. That's very tricky on something like a GPU, because you can't do different operations on different data at the same time. Okay, to a certain extent, if those of you are really into your CUDA stuff, maybe you can spin up different kernels, but there's lots of overheads with that. It's not the same as having completely independent threads. On the IPU, however, as we see here, compared to the GPU, this really suits us well. We can do that group on these cores, that group on those cores, no problem whatsoever. So as you see, in the end, we get somewhere between 4 and 100 times the throughput, depending on how grouped or separated these convolutions are. So on the left, we've got fully depth-wise, so like efficient net uses where you just got groups of depth 1. So every layer is a separate group effectively. And on the right, we have normal ResNet. There's only one group and it's the full depth. So in the middle here is where we, so in the middle and towards the left, where we really see big step ups with that. And this sort of translated into real world, real model advantage. See here that much more so than with the standard ResNet case, we're getting much lower latency and still quite a lot higher throughputs on inference there. And Quant, a European search engine. We've been doing a lot of image search capability things with ResNext. This is the next generation one with the group convolutions on the IPUs, and out of the box without really having to do an awful lot of optimization or spending lots of time playing around with that. They're straight away getting really, really good performance. So just go through a few more of these in general, where we're seeing large performance gains on a variety of different types of models. And this is where we put the fun into fundamental IPU advantage. We have our top left, we've got a variational autoencoder model. For training, we're getting just over 4 times faster training. But this is on one IPU rather than a whole card. So where the card power, the maximum power draw is about 300 watts, but the same as your equivalent GPU in a server, that card has 2 IPUs on it. So if your model is on one IPU, you're only drawing 150 watts. So this 4.3 times faster time to train is also drawing half the power. So win-win. To the right, we have LSTM model for inference. Again, here we're getting hugely higher throughput and at lower latency as well. So again, win-win. Reinforcement learning at the bottom left, again, we've got a huge advantage on the training time to 13 times faster. And efficient net, again, one of the next generation kind of models that can really take advantage of the IPU architecture. This is where we have the fully depth-wise separated convolutions. Again, it's enormously higher throughput at even more so lower latency. It's really good. And a few more here again, we see some really good gains in Markov chain Monte Carlo training for sort of finance calculations. ResNext, as we say, for the image processing, and also BERT for natural language processing. So some big gains there. But that's not just the hardware as well. We've made an awful lot of software gains and continue to do so. So all of these here show you latency and throughput or various kind of performance metrics between our last version of the SDK from earlier in the year and our more recent one from end of first quarter. And across the board here, we're making some really good gains on the software side as well as just having a hardware advantage. So this extra performance is continuing to be optimized and tweaked, and lots of new features being added all the time, which can really help get the best out of the hardware. And just so you say you come along and you say, but I've got my TensorFlow model and it's all been written, all runs nicely on my GPU, and I don't want to go trashing all of that and start writing again for a new architecture. That's the last thing you want to do. Well, that's not necessarily what you're going to have to do. So we'll show here an example of some MCMC example for a financial application, all written in TensorFlow, and show you how much gain you can get while changing so little. So I won't go through loads of the code because that's going to really be a bit dry, but we'll have a quick look here. So here's some of our code. So at the top, I've imported some IPU specific. So this is our IPU TensorFlow port. So I've imported the specific libraries we want there. In the welcome message, I've changed the word GPU to IPU. That's not really, that doesn't really count. Later on, there's a GPU specific config. Yeah, we can get rid of that. We haven't got a GPU on here. And then I add in a couple of lines to define just how the IPU wants to compile the model. So it's just a couple of lines added in there. And here, because we've run something in a function so we can compile it with the IPU, we've indented a little bit and we've just got our config to say, right, give me 1 or 2 or however many IPUs you want, configure the system, and away you go. And that's it. And from here, we see out the box almost a 10 times faster runtime. So that was without any optimization being done. That was a relatively standard off-the-shelf kind of application that the customers are using. And straight away, we saw a really, really nice boost in performance. And to note as well, this is running on 1 IPU versus 1 GPU. So again, 150 watts versus 300 watts. So if you're worried about the power usage and so on, that's better performance at half the power, which is great. But really what we want to see is what people, other than ourselves and current customers, what are our new customers, anybody else in the world, what are they going to do with it? It's really exciting to see in the future what we're going to look back at this and see, wow, they did that with it, they did this with it. It's really, there's going to be so many applications that might not have thought about before, that it's going to be really nice to see what people end up using these things for. One example that's quite cool, I think, is Microsoft have been doing a lot of medical imaging work. So they've been using the IPU servers on Azure. So we'll get onto how to get access to an IPU in a moment, but there's plenty of these on Azure, and they were using this for doing chest X-ray type things for COVID type analysis. And they're trying to do for a COVID pneumonia type classification model, comparing this to B100 GPU. And as you see on the bottom right there, we're getting 2,000 images per second processed versus 166. And we'll say that generally any of these benchmarks over here, we've got this performance over that performance and so on. That does mean we've trained it to similar levels of accuracy. We haven't just trained for the same amount of epochs, regardless of accuracy. It will be trained to completion. So that's really getting a really, really good boost on a topic that is rather prevalent at the moment as well. Okay, so Alex, how can I get one of these IPUs to play around with? Well, good question. So different ways to do this. You can buy IPU in the cloud type access via Seroscale. You can buy a physical server like the one on the right with 16 IPUs, so 8 cards all plugged in from Dell, or you can sign up to Azure for the IPU preview and get your things running on there. Currently, it's a preview on Azure at the moment, but so you need to sign up and be processed and go onto there. But there's lots of ways that one can get access to these, and we really look forward to seeing what you and other people can get running on these things. Okay, so just to briefly summarize, and then I'll see all the questions. This is a fundamentally different processor designed for machine intelligence, machine learning, AI applications. It's not a GPU with knobs on. This is a very, very different philosophy entirely. On current and especially next generation models, we're outperforming leading GPUs. Natural language processing, for example, image classification, and really to a very large extent, some of these finance customer models are really, really much faster on the IPU. And as we say, it's available today for on-premise or cloud-accessed data servers. Please do keep in touch with us. I believe the organizers are also sharing the Twitter and the LinkedIn and whatever else kind of links around. And other than that, all I can say is thank you very much for listening.